Yeah, hello everybody. In this video, let us see about the scaled dot product attention introduced in the transformers architecture of the attention is all you need paper. So, as we know, this transformers architecture has been proposed mainly to handle the sequence data. Let us consider for our example the sequence to be a sentence and its length will be t. Let us assume its length as t, and each of the token is of length d. Okay, the scaled dot product attention takes input as the primitive embeddings of each of these token t embeddings and outputs the more matured tokens of the same sentence of the same length, same shape also. Okay, and in a way, this scaled dot product attention, what it does is, it is more or less like a weighted sum of the input embeddings. Now let us see more in detail how this weighted sum happens. The scaled dot product attention has three stages. In the first stage, we take three matrices WQ, WK and WV. All these are learnable matrices, and we multiply this matrix with each of the tokens H0, H1 to HT. Okay, and upon multiplying with three matrices, we get query, key and value for each token, and the dimension is the same. The intention of taking these three variants of each embedding is that we use query and key of these embeddings to calculate the weights, and we assume the value vector is in a way the input vector itself. So we calculate the weight, multiply the weight calculated using keys and queries with the value vector to get the final embedding output. Now let us see what happens in the stage 2. In stage 2, weights are getting calculated. So what it does is, in order to calculate the weights for 0th embedding, you take the 0th query Q0 and multiply it with each of the available keys K0 to KT. Multiply in the sense dot product. Okay, when we dot product it with t keys, we get a vector of length t. So each dot product gives rise to a single real valued number. So it gives rise to a vector of length t. The next step that we do is scale it with the dimension of each of the embedding, that is d, square root of d, and upon applying softmax we get alpha 0 to alpha t for 0th embedding. Now similarly we can do it for the first embedding also, where we can take Q1 first query and we can multiply it with dot product with all the keys that are available, and it leads to a vector of length t. Upon applying softmax, after scaling it with root d, we get the weights for the first embedding. Similarly we can do it for all the embeddings, gives rise to the weights corresponding to all the embeddings. Okay, this is the stage 2. Weights calculation is done. Now in the third stage, what we do is, we take the value vectors which we have calculated in 0th first stage, and we multiply it with the weights calculated in the second stage. If you can see here, these vectors, 0th vector, first vector to tth vector, we multiply it with the weights of corresponding to each of the vector of the 0th embedding. Similarly we calculate the weighted sum of the first embedding, and similarly we calculate the weighted sum for the tth embedding also. Upon calculating the weighted sum, this is the output embedding. This is the direct weighted sum of the each of the embeddings. Okay. Now let us see how this is represented in a matrix form. Now stage 1. In stage 1 we can see that this H naught is getting multiplied with WQ to gives rise to Q naught. Now let us write this in the matrix form. H naught gets multiplied with WQ matrix, gives rise to the Q naught. Now we can vertically stack all these H's. H means input embedding, primitive embedding. Upon stacking vertically, you get a matrix, H matrix. We can multiply directly with WQ, will gives rise in the Q vector. It is just the same matrix multiplication. We have just parallelized it in a single matrix. We can write it as Q is equal to H into WQ. Similarly, we can calculate K, a key matrix, which is also the matrix multiplication with the same primitive input embedding with WK, and the value vector is also similarly we calculate. Okay, this is the stage 1. In stage 2, we calculate the weights. If you see here, so for calculating weights, what we do the dot product with between queries and keys. For 0th embedding, we are dot producting Q0 with all the available keys. Let us see how that is happening as a matrix multiplication. Take the Q0, take all the keys. This is the K matrix transposed. If you see here, K0 to KT will be arranged in a horizontal fashion. Because if we want it in a vertical fashion, take the transpose of it. Upon multiplying Q naught with K transpose, you get the Y naught. Y naught is the vector that is before softmax. Okay. Y naught to Yt for the 0th embedding. Similarly, we can extend it to all the embeddings also, just by stacking vertically all the input queries. So we write Q0, Q1 up to Qt. Upon multiplying it with K transpose, we get a Y vector. Now we can scale it with root D and apply softmax to get the alphas. All the weights of all the embeddings will be available in this alpha vector in a horizontal way. The first row will have the weights for the first embedding, and last row will have the weights for the last embedding. Okay, and the third stage is calculating the weighted sums between alphas and the value vectors. Now let us see how that stage 3 happens. For 0th embedding, you take weights alpha 0 to alpha t, and value vectors we can stack it vertically, v0 to vt as shown in the here in the figure. If you see here, alpha 0 is getting multiplied with the 0th element of v0, and alpha 1 is getting multiplied with the 0th position of the v1, and all these values are getting summed to produce the 0th value of the output z0. Similarly, we can also see here alpha naught is getting multiplied with the 0th value of v0, and alpha 1 is getting multiplied with 0th value of v1, and similarly all these are getting multiplied to produce the first element of the z0 vector. So this is how the weighted sum is happening. Now if we stack all the alphas vertically and multiply it with the v vector, we will get the z vector output. This is the output of the attention model. So we can write it in a single format like this, in a single sentence format like this: attention of q, k and v is equal to softmax of q, k transpose divided by root d into V. In the paper they have given this formula directly, they haven't explained how this is coming, what is happening, how the vectors are getting multiplied, etc. But we can see it here, it is just a weighted sum of the input vectors, input primitive vectors to produce the output primitive vectors, output matured vectors. Now let us see the summary. So basically scaled dot product attention is just taking the primitive embeddings of a given sentence and it outputs the matured embeddings of the same sentence, and it has 3 stages, where the first stage calculates the queries, keys and values, the second stage we calculate the weights, and in third stage we calculate the weighted sums, which finally produces the matured vectors, matured embeddings of the given sentence. Thank you so much.